Greetings and welcome. In today's video, we're going to continue our analysis of polar equations and their graphs. And we're going to start with just a look at roses and the number of petals that they have. So here I've got kind of like a dynamic function in which I can kind of have these sliders and track the number of petals based off of the value of n. Now, we were told that n was restricted, where it had to be a positive integer, so that's kind of what I've got this doing here, where it's rounding this to a positive integer automatically for us. So you can see when n is 1, I have a single petal, or, we'd technically just call that a circle. When n is 2, it goes to 4 petals. When n is 3, it's 3 petals, so we've got some unusual behavior here. It's not consistent, it seems. When n is 4, that looks like 8 petals. When n is 5, I've got 5 petals. So it's definitely having some irregular behavior here, but perhaps you've spotted a pattern. When I have 6 for the value of n, it looks like I've got a total of 12 petals here. And 7 is 7, and then 8 would actually be 16. So looking at that result, perhaps you can guess what the pattern might be. And it turns out that when n is even, what did we see? We saw that when n was even, the number of petals was 2n, right? So the number of petals is 2n. And when n was odd, the number of petals was n itself. All right, so that's kind of, switching to the wrong thing. And so you can see at 1 we had 1 petal, at 3 we had 3, at 5 we had 5, at 7 we had 7. Now, one of the things I want to point out about these odd petal situations, if I actually start tinkering around with the values of A and B, you can actually end up with some unique situations where you have inner petals taking place. And it turns out for the odd situations, it's duplicating each loop twice is what's occurring. And it just happens to be mapped on top of itself. And when I have some different values of A and B here, we can actually see that this same area is mapped twice. I think this little petal here is a result of the angles over in this portion, and there's probably just a negative R value that's looping that. So one of the ways we can kind of see this, I'll throw a little point on my graph, and I'll animate it. And you can see that it's moving along the curve. Let's see, I could speed that up a little bit. And it does kind of a big petal and then a little petal, I believe, is the pattern. So it goes through that. And if I go back to kind of our original values when A was 0, I believe we'll see that it'll loop each curve. It technically occurs twice for the values of 0 to 2 pi. So that's kind of an interesting thing that you're able to see that a little bit there. Another thing that I want to point out, let's see, I can delete this point. Oop, deleted too much. Is let's actually analyze what these values are doing. So not only can I figure out how many petals I have, but look at what this value of B seems to do. The value of B, let's see, when B is 1, now look at the petals where they are. B is 1.5, B is 2, B is 2.5, B is 3. It appears as though B is controlling the length of the petal. All right? Or at least for values when A is equal to 0, B controls the length of the petal. All right? However, let's say I have the value of A is 1 and B is 1. We can see that the length of my petal is actually A plus B, 1 plus 1. And let's verify that. So my petal is 1 plus 1.5 is giving me 2.5 for the length of the petal. Or 1 plus 2 is 3 for the length of the bigger petal in this instance. So I can actually have the length of the petal is A plus B. All right, and let's actually verify that is also the case even when A is bigger than B. So 3 plus 1 is 4, and that is in fact where we're at. So the length of largest petal is A plus B. And then let's take a look at this. In some of these situations, we actually had smaller petals. Or in this current situation, we have a dimple. So you can see that the dimple, its inner point is at 2 here, and you might be able to guess where 2 is coming from. It's coming from A minus B. And to verify that, let's try some different values. So 3 minus 0.5 is 2.5. 3 minus 0, right? There's no dimple whatsoever. And then, yeah, 3 minus 1.5 is 1.5. So I'm getting different values. And then when they're equal, that's when I actually have a cusp in my graph. And you can actually see the cusp better in a single petal where I have a cardioid taking place here. So let's see. Let me drag this back out. So it looks like the inner value is going to be A minus B. What about, I think I was able to have inner petals here. So it looks like inner petals occur whenever B is bigger than A, right? At least for an odd number of n. And the length of those inner petals, 3 minus 1, is 2, or technically, it is in fact A minus B again. 1 minus 3 is negative 2. This curve here is traced when I'm considering angles over in this region, and they happen to have a negative length of 2 here. And let's see, let's try an even number for n. So I've got 8 petals here showing up once again. And we can see that the smaller petals are in fact going to be an A minus B situation. So this petal here is actually traced for these angles, and this petal here is being traced for these angles, and we just have a negative R value that's taking place there. So it appears as though the smaller petals is A minus B, right? So I'm able to gather that information. And then there's other facts that we were able to look at. I mean, you could figure out, when A and B are different, you can have small petals, big petals. When they're the same, right? We can actually have a cusp situation occurring. When B is less than A, that's when you'll kind of have the dimples occurring in your curve. So we can kind of have all sorts of unique situations occurring. But I think we've analyzed enough with this particular equation for now. But there is much more that you can kind of gather from this. Let's see, the next thing that I want to do is solving systems of polar equations. So in this case, we're actually going to be looking at 2 equations at the same time and trying to figure out where do they intersect, where do they occur at the same time. And there's 2 ways we'll be able to do this. The first way we'll solve algebraically, and then I'll show you how to do it using some technology. We can use the graphing calculator, and I'll use Geometer Sketchpad as well. So, I could call this find the intersection or solve. And likely with, these petals, there's many locations that they could intersect with one another. So I'm expecting that there's probably more than one intersection, depending on how these were set up. So let's see. Let's find the intersection between the 2 equations. R equals 3 minus 3 sine theta. and r equals 4 minus sine of theta. So let's see. So one of the ways we could do this is algebraically. So let's do that first. And what I'm going to do is solve this just as I would a regular system. And in this case, I'm going to solve by substitution, since I can realize that both of these are equal to r. So I could actually I'll do this one. So if this is equal to r, I can use my little Indiana Jones property substitution, right? Switch out the bag of sand for the golden idol, and plug this in for r entirely. So 4 minus sine theta is equal to 3 minus 3 sine theta. So I think it's probably valuable for us to gather our signs together, right, and do some manipulation here. So let's see, what should I move around? I think I'll add the 3 sine theta to both sides. And we'll have 4 plus 2 sine theta equals 3. So here we're going to end up having to use some of our solving trigonometric equations skills in order to do this properly. So I get equals -1, and then of course I'll divide by 2. So I get sine theta is going to equal -1/2. So my first question that I want to consider is the sine of an angle equals a negative number in 2 particular quadrants. So I'm expecting this to be in quadrant 3 and quadrant 4, right? Because sine is positive for quadrants 1 and 2. And what I would do here to get theta by itself is sinverse or sine inverse both sides. And I get theta equals, so I've got sine theta is -1/2 in 2 instances. Now the reference angle, I guess I'll call it alpha, is going to equal, sine is 1/2 at 30 degrees. So we want to figure out what is that in the 3rd quadrant, so that would be 180 plus 30. And what is that in the 4th quadrant? That would be 360 minus 30. Oh, well, you know what I just realized? I want to work in radians, and I jumped right into degrees there. But yeah, let's work with radians. So sine is 1/2 at pi over 6. That's more like it. So in the 3rd quadrant, that would be pi plus pi over 6. And in the 4th quadrant, that would be 2 pi, right, which is the same as 360 degrees, what I was just writing. I'm just doing it in radians now, minus pi over 6. And it looks like I'd have to do a little bit of common denominator work here. Multiply by 6 over 6. Here I'd have to multiply by 6 over 6. And I'll get 6 pi plus pi is 7 pi over 6. And over here this would be 12 pi minus pi, so that's 11 pi over 6. So theta is going to equal 7 pi over 6 or 11 pi over 6. So once again, like I said, it's possible to have multiple solutions. Now I didn't yet solve my system. I just found out what angle these equations have the same point at, but I still have to figure out what's the r value for these. So one of the things I could do is plug this into either of the originals and get the r value for them. So let's do the 3 minus 3 sine theta. So let's see. So I'll plug that in for, so r is equal to 3 minus 3 sine of 7 pi over 6. And the other one is r equals 3 minus 3 times sine of 11 pi over 6. Now, I guess technically I already kind of calculated these values for sine. So 3 minus 3 sine of 7 pi over 6, well, the reference angle was pi over 6. It's going to equal 1/2. It's in the 3rd quadrant, so it's -1/2, right? We kind of knew that up here. So this is negative a half. I might as well do some work over here as well. 3 minus 3 times negative a half as well here. So r equals 3 plus 3 halves. R equals 3 plus 3 halves. It looks like these are going to be the same number, but remember they're at different angles, so it's not talking about the same point. So don't assume that just yet. And well, I guess I can work with decimals here, since we typically, when graphing these, are interested in decimals anyway. So 3 plus 1.5, this is 4.5, and this is also r equals 4.5. So my solutions in r theta are 4.5 comma 7 pi over 6 and 4.5 comma 11 pi over 6. All right, so this is how I could do this algebraically, all right, where I just used substitution and did it from there. The other method I could use is graphically, which one of the things that's tricky is, since for instance, this point right here, 4.5 7 pi over 6, is the same as negative 4.5 comma pi over 6. Since there's multiple ways of matching the same point, it's possible I could be looking at a graph where it appears as though visually they cross paths, but maybe on one graph it had a negative radius at the time, and the other graph had a positive radius, and they might not technically be intersecting. So when I'm solving graphically, if I'm using a graphing calculator or Geometry Sketchpad, I'm going to have to somehow trace my values in order to do that correctly. So let me pull up my graphing calculator here first. Let's see, looks like, all right, so you guys can see that. So just to clarify, I'm in polar equations, and I've switched this to simultaneous graphing. That way I can see both curves being plotted at the same time, so I can kind of have a guess whether or not those points are going to land on top of each other at the same moment for the same theta values. So I've got that set up. So for y equals, let's plug these in. So what were my equations? It was 3 minus 3 sine, and to get theta, it's just going to be this, my variable button, xt theta n. So there's theta. And my other equation was what? 4 minus sine theta. And I can close that parentheses there. Now, also, just to verify, when I was in mode, I am in radians. So when I go to graph this for window, my theta values are between 0 and earlier I'd made the mistake of having 360 plugged in, which was embarrassing. So you have to make sure that this is 2 pi when you do that. And then for the theta step, I just gave it a small number. I did pi divided by 180, which is technically a degree, right? Or 0.017 radians. My window, well, I'll start off with a zoom standard just to show you what we've got. So we've got both of the equations being graphed simultaneously. You can see that it appears as though they both crossed here, which is at 7 pi over 6, and at 11 pi over 6 right there. Now, technically, this isn't, I guess, proportioned correctly. One of the things you can do is if you hit zoom and go down to z square, the fifth option, it will make sure that the number of pixels horizontally and vertically line up so that these are kind of correctly proportioned. So this is actually a circle and things like that. And then I can go to trace, and right now I'm on my R1 equation. And if I hit right, it'll cycle through values of r and theta. And you can see me kind of going around this cardioid. And I want theta to be, back it up, backing up. And I get r equals 4.5 right here at 3.665 radians, which I believe is probably 7 pi over 6. But that's for the first equation. So to switch between equations, you can use the up or down arrows. So when I hit up, notice equation 2 has exactly the same points. So that is in fact an intersection that's occurring there. And then let me loop around here. So going around, going around. Oh, I think I went too far. Backing up, backing up. And here 5.7595865 radians is in fact going to be 11 pi over 6, just under, right, 2 pi radians. And if I hit down, you can see equation 2 has exactly the same value. So it is an intersection occurring there. And just to verify that, let me go to a different point. Oh, it looks like I maxed out. So you can see that my little crosshairs, if I hit up and down, it's bouncing between those two. So the value of theta is the same, but you can see that the r value is different, verifying that that is in fact not an intersection. All right, so you can find these intersections using a graphing calculator a little bit, or at least for the sake of verifying. Let me actually grab a screenshot of this, and I'll just throw this right into my notes. Why not? And thing of beauty, thing of beauty. And then the other thing, I believe I have on a separate. Let me verify here. Here's my same equations graphed out here. This one's a little bit trickier to get it to trace properly. I'm going to have to do some more practice with Geometry Sketchpad. But one of the things you can do is kind of make a point and drag it around. And I could even find the, let's see, measure coordinates. So here's point C, and its coordinates are there and there. And as I drag point C around, you can see the coordinates are changing. And when it's at 4.5 for the R value, the radians, that's actually one of the things I found unusual. When you're in the third and fourth quadrant, it chooses to give you negative radians rather than ones that are greater than pi. And let me throw another point in here on my second curve, the cardioid, and measure coordinates. So there's point D, and let me drag this point, and we'll see that in fact they do line up right at 4.5. Bam. So those are in agreement. So I can I don't have as, or at least I'm not familiar as much with a better tracing means in Geometry Sketchpad. For rectangular or Cartesian coordinate systems, sometimes you can select your two functions and just click construct intersection. But I tried to do that on these two, construct, and it is not an option for polar equations on this. But it does in fact work out. I just wanted to point that out. So here, let me actually drag. Where's point C? They're slightly off. And let's see. Just for the sake of the screenshot, now I'm just being picky here, aren't I? And we're good. So let me grab a screenshot of this, throw this in my notes, just so you can see two different ways that this is done. Thank you for watching. I hope that this explained how you can solve systems of right equations in the polar system. Let's scale this down. And also just gave you some interesting facts about the number of petals, the lengths of petals on some of these, having some interesting effects there. So thanks for watching. I'll talk to you guys next time.